Hello, good morning, afternoon or evening, depending on the time you are watching this video. This is our video 11. We are discussing filter. Filter is a frequency selective network. Filter allows certain frequencies to pass. Filter blocks certain frequencies. You remember transfer function, H, which is the ratio of the output over input. In the pass band, H can be close to 1, so it allows that pass band frequency to pass. In the stop band, H can be far less than 1, so it multiplies the input by less than 1, so it will block that frequency. Now, the characteristic, the ideal characteristic, we have low pass filter is like this, where this will be 1. This is H. This is low pass filter. This will be the cutoff frequency, or FC. This is high pass. So this is H. This is H. H will be 1 here. This is omega C or FC, and then we have band pass filter. This is omega C1, FC1, omega C2, FC2. This will be 1. This is H. This axis is the frequency axis. That's the frequency axis. That's the frequency axis. Then we have band reject filter. This is band pass filter. Band pass filter. This is band stop filter. We have this is 0, this is frequency 0, frequency 0, this is 1, omega C1, FC1, omega C2, FC2. This is the axis for frequency. Hello, on the y-axis, we have H, which can be referred to as amplification. That is H. You can use A to also represent it. That is the y-axis. The quantity we have there is the ratio of output over input. Like I've said in one of the lectures, this can also be expressed in terms of gain. G, which is 20 log H to base 10. Now, the y-axis is either amplification, which is gain, or amplification, which is H, or it is gain, G, which is 20 log H over 10. Now, that's your y-axis. Your x-axis is frequency. Your frequency can be in hertz if we are using FC. That is, if we are using F. If we are using F is in hertz. F is in hertz. We can use omega, which is in rad per second. So as you follow this lecture, know that we have two possibilities on the y-axis and we have two possibilities on the x-axis. So both possibilities are related to each other. Let me come again. If you want this axis to be amplification, A, it has no unit, because it is just output over input. It is output over input. You can refer it to as H. You can also refer it to as amplification, A. That means the output coming out is input multiplied by A. If it is the frequency we want to pass, we make A to be 1. If A is 1, it means the output will be equal to input. If it is the frequency we don't want to pass, we want to block that frequency, we can make our A to be 0, we can make our A to be 0. If we make our A to be 0, 0 times input, that will give us no output will come out. That is how it allows certain frequencies to pass and it blocks certain frequencies. Let me explain again. The way the filter does is that it has different value of A for different frequencies. For the frequencies to be passed, it can make A to be 1. It can make A to be 1. So if A is 1, whatever is the input is multiplied by 1 and becomes the output. But for the frequencies we want to block, we can make A to be 0. If we make A to be 0, whatever the input is times 0, the output is going to be 0. So it is blocked. So you see here, this place is the pass band. This is the pass band. The A is 1. The A is 1 in the pass band. A is 1 in the pass band. This place is the stop band. Stop band. A is made 0. That is for low pass filter. For high pass filter, in the lower frequency, the amplification is 0. In the upper frequencies, the amplification is 1. And like that. So this is how your filter works. It gives different values of A for different frequencies. Let me ask you again. For the frequency we want to pass, what will be the A of the filter? The answer is that the A of the filter for the frequencies we want to pass is 1. For the frequencies we want to block, what will be the A of the filter? The A of the filter in this case is going to be 0. So that's why in the band pass filter, here the amplification is 0. Here the amplification is 1. So it will allow these frequencies to pass. Here the amplification is 0. It will block this frequency. And like that. Now, this our H can be A, can also be expressed as decibel. So the unit, if it is expressed as a gain, the unit is decibel. If it is expressed as ordinary amplification, it has no unit. So if it is expressed as a gain, the unit is decibel. So now, these are ideal characteristics. These are ideal characteristics which are not possible in real life. In real life, let me use color to indicate what is possible in real life. I will use red. You can have something like this in real life. You can have something like this in real life. You can have something like this in real life. You cannot have sharp rising and sharp falling. So this brings us to what we call, for example, in real life, you can have something like this. So what I draw with black, they are ideal characteristics. They are not possible practically. What I draw with red, they are approximate. They are approximate or practical characteristics. Now, certain researchers in those days, certain old people, they are giving us some approximation functions. Approximation functions. That is functions that can try to approach the ideal, but they cannot be ideal. So we have approximation function. Example of approximation function is what we call Butterworth functions. Butterworth functions. Butterworth function. We have Chebyshev. We have Chebyshev. We have Chebyshev. We have elliptic. Elliptic. These are different people who have given us different approximation formulas. In this video, we are going to demonstrate Butterworth. We are going to demonstrate Butterworth approximation. We are going to demonstrate Butterworth approximation. If you check the Butterworth, there is what we call Butterworth table. Look for the table. The first line on the table, when n equals to 1, is written as s plus 1. That is telling you that the filter function is 1 over s plus 1. What they write in the table is the denominator, that is written on the table. This is what we find in the table. But when you want to interpret it, the filter function is going to be 1 over that denominator. So h of s equals 1 over s plus 1 for n equals 1 or order 1, first order. So if that is the first order, then s is actually equal to j omega. S is equal to j omega, where omega is the frequency. Omega is the frequency in rad per second. Omega is the frequency in rad per second. Omega equals 2 pi f. That means f is omega over 2 pi. This is also frequency. We can express our frequency either as omega, which is in rad per second, or we can say omega equals 2 pi f. That means f equals omega over 2 pi hertz. You can express your frequencies in that way. That is the x-axis. Now, we can now substitute. We can say that h j omega equals 1 over j omega plus 1. So, we can look for the magnitude alone. Magnitude alone is going to be 1 square root of omega squared plus 1. So, we can plot. By graphing, I mean we can plot amplitude hj of omega. We can plot it versus omega. Or we can plot amplitude equals hj omega. We can plot it versus frequency. We can plot it against omega if we like. We can plot it against frequency if we like. For example, now if we want to write this as frequency, what do you write? You will write that 1 over square root of 4 pi square f square plus 1. I hope you can capture it. Now, if you use this expression, you are plotting against omega. If you use this expression, you are plotting against f. Both are possible. Now, I want us to generate 4 graphs for the same function. The other possibility is that this is the y-axis. We can express A as, we can plot 20, we can plot gain 20 log h j omega to base 10. which is same thing as 20 log 1 over square root of omega squared plus 1. In this case, we are plotting gain versus omega. This is the first graph, graph 1, graph 2. This will be graph 3. We can plot graph 4. We say that gain equals 20 log 1 over square root of omega square root of 4 pi square f square plus 1. This is gain versus frequency. Versus frequency. Hello? So this is our graph 4. This will be our graph 4. So this will be our graph 4. Graph 4. Hello? The same low pass filter. The same low pass filter. We can plot, we can use 4 graphs to illustrate it. Either we say amplification versus omega, graph 1, amplification versus frequency, that's graph 2, gain versus omega, gain versus. I hope you know that these things are related to each other. So the 4 graphs are actually saying the same thing in different ways. Now, like we have done in class before, you can substitute. You can start plotting. How do you plot? Make your omega to be 0, 0.1, 0.2, 0.3. Calculate A. What will A be? For this, what is A? What is A? And then you graph. And then you what? You graph. You graph. And then you graph. Now, when you graph, what graph are you expecting? You are expecting something like this. It will be we are expecting practical characteristic. We are expecting practical characteristic, not ideal. Ideal is, remember, ideal is this black. Ideal is that black. Whereas what you are going to get is red. We will now come to the computer. I've prepared programs, computer program in MATLAB that will plot this graph for us. On your own as students, like we have demonstrated in class, we have plotted this graph in class. I now want to use computer to draw it. I've developed some programs using MATLAB. So I will take you to my system now. You are going to see the curves the way they are. My cameraman, picture the screen. Now you are welcome to MATLAB. This is my MATLAB interface. I've developed 4 programs to do this. The expression that you have, let me show you the first program. Now, if you look at this expression, can you see the arrow? This expression is the same as this. It's the same as 1 over omega square plus 1. This is what I've written. This expression is what I've written on this line. You can see that I wrote h. You can see that I wrote omega and I square it. Don't worry about this of k. What of k means is that I work for omega of 1. When omega is 0.1, I will get h of 1. That is h when omega is this. If omega 2 is 0.2, I will get h of 2, which is that. So what I'm trying to do here, so that k you are looking at, don't worry about it, is to now start tabulating. It's like I'm having W1, W2, W3, W4, and I'm getting H1, H2, H3, H4, which I'm going to plot. So I've embellished. Let me show you the program completely. I will send the program to you separately. So this is a program. This one will draw the first, this one will give us the first curve, which is amplification versus omega, graph 1. So I will come here and I will run the program. You will see a graph sheet coming up. The name of my program is, the first program, LP FB N1. I name it like that. I name it like that to show that I'm working on low pass filter. I'm working on low pass filter. I'm working on low pass filter, which is Butterworth, and N is 1. N is 1. So like that. If I run it now, if I run it, you see the graph that is coming up. You see the graph that comes up. So this is the graph. Bring the video closer. Bring the camera closer. You can see I have filter amplification here. I say it has no unit because it's the ratio of output over input. And then here I'm having, this is the plot. Initially, this is the pass band. This one you are seeing, I've told you in class before, for a Butterworth filter, the cutoff frequency is 1. The cutoff frequency is 1 rad per second. This axis is frequency in rad per second. The cutoff frequency is when the cutoff is when the amplitude becomes 1 over root 2, which is around 0.7071, something like this. It is at that point that we call the cutoff frequency. You can see that this is 0.7 something. Let me calculate what it's actually supposed to be. It's supposed to be 1 over 2 raised to power 0.5. So the figure is actually 0.7071. So let's go back to that our graph. This is our graph 1. So I wrote it here that this is a low pass filter Butterworth. Order 1, n equals 1. Cutoff frequency is omega c equals 1 rad per second. So the cutoff frequency 1. It is at this one when in the pass band, the amplification is 1 or a bit less than 1. By the time it drops to 0.7071, then we have reached the cutoff. So from here to here is the pass band. From here to here is the stop band. So that is the first graph. We have plotted A versus omega.